Right now, at this precise moment on October 28th, 2025, something is happening 130 million miles away that we cannot see. The interstellar object designated 3I, Atlas reached solar conjunction on October 21st. It slipped behind our Sun, vanished from every telescope on Earth. And yesterday, October 29th, it passed through perihelion, the optimal point for what astronautics calls an Oberth manoeuver, the most energy efficient moment to alter a trajectory using gravitational assist. For 8 days, this 5-kilometer visitor from another star system has been hidden from observation, bathed in 33 gigawatts of solar radiation, 1/3 of the total nuclear power output of the United States, travelling at 68 kilometers per second through the perfect blind spot. Two things about that timeline are difficult to ignore. First, the conjunction and perihelion are separated by exactly 8 days, creating a window that aerospace engineers would describe as ideal for unobserved trajectory modification. Second, 3I Atlas will not re-emerge into Earth's morning sky until November 11th, giving us no way to verify its exit vector until then. What we cannot observe, we cannot rule out. The discovery came from the Asteroid Terrestrial Impact Last Alert System facility in Rio Hurtado, Chile, on July 1st, 2025. Routine survey work. The object was 4.5 astronomical units out, roughly 420 million miles from the Sun, moving inbound at 137,000 miles per hour, fast enough that orbital dynamics immediately flagged it as hyperbolic. Unbound. Not from here. The designation followed protocol. 3I for third, confirmed interstellar object. Atlas for the discovering instrument. Within 72 hours, pre-discovery observations emerged from archives at Palomar's Zwicky transient facility and 3 separate Atlas stations worldwide. Backtracking the trajectory confirmed extrasolar origin with certainty. It came from Sagittarius, from the dense star fields toward galactic center, where tracing a single point of origin becomes statistically meaningless across 10 million astronomical units and potentially millions of years of drift. No parent star has been identified. No encounter with any catalogue stellar system shows meaningful perturbation of its path. It simply arrived, following a line that brought it within 5 degrees of the ecliptic plane, the flat disk where planets orbit. That alignment is the first anomaly. Think of it like this. If you fired a bullet randomly into a room, the odds of it passing within 5 degrees of horizontal are roughly 0.2%. Random interstellar objects should arrive from any direction with equal probability, distributed across the entire celestial sphere. Instead, 3I, Atlas, came in low and flat, threading itself into planetary space, as if selecting an insertion corridor. Not impossible, improbable. Hubble Space Telescope imaging on July 21st revealed the second anomaly, a forward-pointing jet, a bright, elongated structure aimed toward the Sun, extending from the nucleus in the direction of travel. Comets outgas, solar heating vaporizes surface ices, and radiation pressure pushes that material away from the Sun into the classic tail. What Hubble saw was the opposite, an anti-tail, a sunward jet. Ground observations from the 2-meter twin telescope at Tidey Observatory on August 2nd confirmed it. 159 exposures showing coherent directional emission that geometric projection effects cannot fully explain. Cometary science has documented apparent anti-tails before, optical illusions created by viewing angle and dust particle trajectories. Those resolve with additional data. This one persisted. Spectroscopic analysis from the Very Large Telescope in Chile and multiple observatories worldwide revealed the third and fourth anomalies: extreme nickel enrichment in the coma and extraordinarily low water content, 4% by mass where typical comets carry 80%, The nickel to cyanogen ratio sits orders of magnitude above cometary norms. Nickel vapor was detected glowing at distances where temperatures should be far too cold for metal vaporization. No accompanying iron signature appeared, which contradicts the typical iron-nickel ratios found in asteroidal and cometary material. The chemistry reads industrial, not conclusively artificial, but statistically deviant. The fifth anomaly emerged from polarimetry, extreme negative polarization of reflected sunlight, unprecedented among all observed comets, including the previous interstellar visitor 2I, Borisov. Polarization signatures tell us about surface grain properties, size, shape, composition. The measured values suggest surface characteristics inconsistent with conventional icy dusty comet models, again explainable with exotic grain populations and unusual formation environments, again sitting at the far tail of the distribution. The sixth anomaly is scale. Hubble observations constrain the nucleus diameter to between 440 meters and 5.6 kilometers. Analysis of the object's trajectory, which shows essentially zero measurable non-gravitational acceleration, implies a minimum mass exceeding 30 billion tons. That makes it 1,000 times more massive than 2I Borisov and potentially 1,000,000 times more massive than 1I Oumuamua. Large interstellar objects should be rare. We should detect 1,000,000 small ones before encountering one this size. We have detected 3 interstellar objects total. One of them is 1,000 to 1,000,000 times larger than the others. The seventh anomaly is the trajectory itself. After initial discovery, orbital integration showed that 3I Atlas would pass Mars on October 3rd at a distance of 29 million kilometers, fly within 64 million kilometers of Jupiter in March 2026, and approach within 269 million kilometers of Earth on December 19th. Not close approaches by collision standards, but planetary flyby geometry for an object on a hyperbolic escape trajectory. It threads through the inner system, encountering 3 major planets in sequence. Random arrivals do not select such paths. The integrated probability of all 7 characteristics occurring together in a natural interstellar comet was calculated at approximately 1 in 10 quadrillion. Let that sink in. Any single anomaly admits natural explanation. Taken individually, each can be rationalized within the bounds of cometary science. Ecliptic alignment might reflect the galactic midplane distribution of ejected objects. Anti-tail jets could result from unusual spin states and vent orientations. Nickel enrichment might indicate formation in exotic stellar environments with atypical metallicity. Low water fractions could mean condensation far from a dim parent star in a cold outer disk. Extreme polarization could arise from carbon-rich dust grains with specific morphology. Large size could simply be observational bias. We see what we can detect. Planetary flyby geometry could be coincidence, a lucky insertion that happens to thread the needle. But stacked together, the anomalies form what analysts call an improbability cascade. The 8th item completes the pattern, the arrival direction. 3I, Atlas, approached from within 9 degrees of the coordinates where the WOW signal was detected in August 1977, the famous 72-second radio burst from Sagittarius that remains unexplained. 9 degrees on the sky corresponds to roughly 0.6% probability by random chance. Adding it to the stack pushes combined odds into the realm where natural explanations require increasingly specific and coordinated circumstances. This is where the scientific method encounters its most difficult terrain. We follow evidence, we build models, we test predictions, but we also carry priors, assumptions about base rates, about what kinds of things exist in the universe. The prior probability that any given astronomical object is technological is vanishingly small because we have never confirmed artificial origin for any celestial body beyond Earth. That prior is strong enough to override substantial anomaly stacks until evidence becomes overwhelming. So the working hypothesis remains. 3I Atlas is a natural comet, albeit a highly unusual one, carrying compositional and structural signatures from its formation environment that we do not yet fully understand. Here is the terrifying part. The Oberth effect is not speculative physics. It is standard astronautics used by every interplanetary mission that performs a gravity assist. Maximum kinetic energy change occurs when propulsive burn happens at peak velocity during closest approach to a gravitating body. For 3I, Atlas, peak velocity was 68 kilometers per second at perihelion on October 29th, hidden from Earth-based observation by the sun's glare, with 33 gigawatts of available solar power illuminating its surface. If the object is technological, if it carried any capacity for trajectory modification, that was the moment and place to execute it. The geometry is optimal, the energy budget is maximal, the observation gap is total. If this were a mission design problem, if you were planning a comet-disguised reconnaissance probe intended to survey the inner solar system, you would arrive on a low-inclination trajectory to access planetary orbits efficiently. You would maintain cometary appearance through passive outgassing during approach. You would time perihelion passage to occur during solar conjunction when Earth cannot observe. You would use the Oberth window to deploy smaller subprobes or alter your exit trajectory without detection. And you would ensure that any maneuver left your post-perihelion path indistinguishable from natural variation within the error bars of pre-conjunction orbital solutions. 3 interpretation scenarios merit consideration. Scenario 1, 3I Atlas is a natural comet with extreme but plausible characteristics. Formation occurred in a chemically unusual stellar environment, perhaps around an older thick disk star with atypical metallicity. The object accreted in a very cold outer region where carbon dioxide dominates over water ice. Long-duration interstellar travel allowed cosmic ray processing and volatile loss, modifying surface properties and producing the observed polarization signature. Arrival geometry is coincidental. Ecliptic alignment reflects slight bias in the galactic distribution of ejected bodies. The sunward jet results from localized active vents on the nucleus surface combined with complex spin states and viewing geometry. Nickel enrichment indicates unusual parent body composition, but not artificiality. This scenario requires no new physics, invokes no extraordinary claims, and fits within the extended envelope of cometary diversity. It is the Occam's razor solution. It is also the scenario that most scientists currently favor. Scenario 2, 3I. Atlas is a natural object but functions as an inadvertent harbinger, not designed, but significant. Some astrophysical process we do not understand produces compositional signatures that mimic industrial chemistry. Some dynamical mechanism we have not modelled generates correlated arrival geometries. The object is a data point revealing gaps in our understanding of interstellar medium chemistry, stellar nucleosynthesis, planetary system formation, or gravitational dynamics. It warns us that our models are incomplete, that the distribution of interstellar material is more complex and structured than current theory predicts. This scenario also requires no technology, but it demands new astrophysics. It suggests that the apparently artificial signatures are in fact natural but previously unknown phenomena. It is a conservative expansion of the natural hypothesis. Scenario 3, 3I. Atlas is technological, or partly technological, not necessarily hostile, not necessarily a threat, but engineered. This scenario subdivides into multiple branches. Branch A, the object is a defunct artifact, a dead probe from a civilization that no longer exists or no longer cares, adrift for millions of years, its systems inactive, its mission long forgotten, arriving in our system by chance, its anomalous properties reflecting its manufactured origin but not present intent. Branch B. The object is an active reconnaissance platform, deliberately targeted to survey our system, using cometary camouflage to avoid attention, executing planned maneuvers during the observational blackout, potentially deploying subprobes toward planetary targets. Branch C. The object is a test, a diagnostic, some form of first contact protocol, approach in a detectable but ambiguous form. Gauge response. Observe whether the local civilization notices, investigates, panics, ignores. Assess technological and sociological parameters before revealing presence. This scenario is extraordinary. It requires accepting that intelligent technological species exist beyond Earth and that one has sent hardware into our neighborhood. It contradicts our complete lack of confirmed artificiality in the astronomical record. It carries massive implications for cosmology, biology, history, and human self-conception. It violates the strong prior that we are alone, or at least uncontacted. But here is the critical epistemological point. Extraordinary claims require extraordinary evidence. But extraordinary claims do not become impossible claims just because they are uncomfortable. The evidence threshold for accepting scenario 3 is very high, much higher than for scenarios 1 or 2. That threshold has not been met, not remotely, but the threshold is not infinite. It can be approached, and the approach happens through accumulation of anomalies that resist naturalistic resolution, through observation of behaviors that cannot be explained by known physics and chemistry, through detection of patterns that show design. 8 documented anomalies do not constitute proof, they constitute a puzzle that most experts interpret as unusual but natural, a puzzle that a minority of scientists argue deserves sustained follow-up precisely because the implications of misclassification are so significant. This is where intellectual honesty demands holding 2 positions in superposition. The most likely explanation is natural, and we should not prematurely dismiss low probability alternatives if they are testable. So here is the countdown. Here is what matters over the next 90 days. November 4th, 2025. ESA's Jupiter Icy Moons Explorer spacecraft, JUICE, passes within 64 million kilometers of 3I, Atlas. JUICE carries the Janus Visible Imager, the MAGIS Infrared Spectrometer, and the SWI submillimeter wave instrument. This will be the first post-perihelion observation, the first data since the object disappeared behind the Sun. JUICE will capture multi-wavelength imagery and spectroscopy at a moment when cometary activity should be maximal. If 3I, Atlas underwent significant fragmentation, if it deployed secondary objects, if its trajectory has changed in ways inconsistent with gravity and outgassing alone, JUICE will document it. November 11th, 3I Atlas re-emerges into Earth's pre-dawn sky in the constellation Virgo, low above the eastern horizon. Ground-based telescopes with apertures of 8 inches or larger will be able to observe it again. Magnitude is predicted to be around 12 to 13, significantly brighter than the magnitude 18 at Discovery, but still requiring telescopic observation. The critical question, does the object's position match orbital predictions calculated before solar conjunction? Trajectory residuals within expected error bars would indicate gravity-dominated motion. Deviations exceeding 3 sigma would demand explanation. Natural causes could include asymmetric outgassing, nucleus fragmentation, or previously unmodeled non-gravitational forces. Unnatural causes would include propulsive maneuvers. November 25th, JUICE performs a second observation session of 3I, Atlas. By this point, the comet will be farther from the Sun, cooling, reducing activity. Comparing the 2 JUICE datasets will reveal whether surface properties, coma, composition, or activity patterns change between early and late November. Sustained anomalies or unexpected brightening would be significant. December 19th, 3I Atlas reaches its closest approach to Earth, 1.8 astronomical units, roughly 269 million kilometers distant. This is opposition geometry, frontal illumination, maximum angular separation, ideal viewing conditions for detailed spectroscopy and imaging. Professional observatories will obtain high-resolution spectra across ultraviolet, visible, and infrared wavelengths. The Hubble Space Telescope and the James Webb Space Telescope have scheduled follow-up observations. Hubble will perform ultraviolet spectroscopy to determine sulfur to oxygen ratios and refine gas composition measurements. JWST will use its NARSPEC instrument to detect water, carbon monoxide, carbon dioxide, ammonia, methane, and trace species. If the compositional inventory shows typical cometary abundances, if the water fraction has increased as expected from solar heating, if nickel has faded and gas emission has normalized, that supports natural origin. If anomalies persist or intensify, the puzzle deepens. January 25th, 2026. 3I Atlas and Earth reach opposition, directly opposite sides of the Sun. Tail structure will be fully illuminated and visible. High angular separation allows tracking of any secondary objects that may have separated from the nucleus during perihelion passage. Sky surveys will search for co-moving bodies, objects following similar trajectories, with small velocity offsets. Tidal forces from the Sun would separate ejected probes over timescales of months, creating detectable trajectory divergence by late January. March 16, 2026, 3I Atlas passes within 54 million kilometers of Jupiter. NASA's Juno spacecraft orbiting Jupiter will turn its instruments toward the comet. Juno carries ultraviolet, infrared, and radio sensors. Radio observation is particularly significant. Natural comets do not emit radio signals. Detection of any coherent radio transmission from 3I Atlas would be definitive. Juno will also measure magnetic field perturbations and charged particle interactions as the comet crosses Jovian magnetospheric boundaries. Beyond March, 3I Atlas will continue outward, fading, eventually crossing the heliopause and returning to interstellar space, never to be seen again. The window to characterize this object is finite. Every observation we obtain over the next 5 months contributes to resolving its nature. 3 monitoring priorities guide observational strategy. First, astrometry. Precise position measurements at every opportunity. Compare observed positions to predicted positions calculated from pre-conjunction orbital elements. Quantify residuals. Model non-gravitational accelerations. Determine whether the exit trajectory is consistent with inbound trajectory plus known forces, or whether unmodeled impulse occurred during the blackout period. Second, spectroscopy. Continuous composition monitoring. Track gas and dust emission rates. Watch for changes in nickel abundance, water fraction, carbon dioxide dominance, and volatile ratios. Measure isotopic signatures if signal-to-noise allows. Compare with laboratory spectra of known cometary analogues and industrial processes. Third, morphology. Image the nucleus, coma, and tail at every opportunity and wavelength. Search for fragmentation, for secondary nuclei, for non-ballistic trajectories, for brightness variations inconsistent with rotation and outgassing. Look for structure that implies control surfaces, attitude stabilization, directed thrust, or geometric regularity. Several ground-based networks are coordinating follow-up. The International Asteroid Warning Network has elevated 3I Atlas to monitoring status. 227 observatories worldwide have registered participation. The Vera C. Rubin Observatory recently commissioned, is conducting validation observations and will track the object through its entire visible window. The European Southern Observatory has allocated substantial telescope time on the Very Large Telescope and the Extremely Large Telescope once it comes online. NASA's Deep Space Network is available for radar observations if the object comes within detectable range, though the distances involved make radar characterization unlikely. Amateur astronomers with moderate apertures are contributing photometry and astrometry through citizen science platforms. The dataset will be comprehensive. If something is there to be found, we will find it. Institutional response has been measured. NASA issued standard press releases describing 3I, Atlas, as a natural interstellar comet, emphasizing that it poses no threat to Earth and will remain at safe distances throughout its passage. The European Space Agency has been similarly straightforward, highlighting the scientific opportunity for multi-spacecraft observations and the insights expected from JUICE and Mars orbiters. No emergency protocols have been activated. No planetary defense measures are under consideration. The tone is routine discovery, interesting object, valuable science. Behind that public-facing calm, there are conversations. Not panic, not conspiracy, but careful consideration. Scientific institutions understand the stakes. If 3I Atlas is natural, it represents a rare chance to study pristine interstellar material and test models of comet formation in alien star systems. If it is not natural, if it is something else, then the implications cascade across every field of human knowledge. So the approach is conservative, evidence-driven, and methodical. Document everything. Apply rigorous analysis. Do not speculate publicly beyond what the data support. Do not dismiss testable hypotheses prematurely. Do not sensationalize, but do not ignore. One particular concern animates the more cautious analysts, the Trojan horse scenario. In ancient history, the city of Troy received a gift, a wooden horse, a tribute from departing Greek forces. They brought it inside their walls. It contained soldiers. The city fell. The analogy is direct. If you wish to deliver a payload into a defended or monitored system, you disguise it as something benign, something expected, something that will be accepted and ignored rather than intercepted and investigated. A comet is the perfect disguise. Comets are common. Interstellar comets are rare, but not unprecedented. They have predictable behavior. They outgas, they brighten, they fade, they follow gravitational paths. They are scientifically interesting but not threatening. They are not examined with the scrutiny applied to unknown spacecraft. So if you wanted to insert probes into the inner solar system, if you wanted to approach Earth's orbit without triggering defense responses, you would build something that looks exactly like 3I Atlas, large enough to carry payload, fast enough to cross interstellar distances, targeted to arrive on low inclination, camouflaged by active cometary outgassing, timed to reach perihelion during observational blackout, designed to deploy subunits during closest solar approach when thermal and gravitational conditions are optimal for separation. This is not prediction. This is scenario analysis. The base rate probability remains low, but it is not zero, and the cost of misclassification, if it is real, is unbounded. So we watch, we wait, we measure, and over the next 4 months, as 3I Atlas traverses the inner system and begins its outbound leg, we will learn whether the anomalies resolve into natural explanations or persist into something that demands revision of our understanding. November 11th is the first checkpoint. When the object re-emerges into view, when we can compare its actual position to its predicted position, we will have the first post-perihelion trajectory data. If it is where it should be, gravitationally speaking, then natural origin remains strongly favoured. If it is not where it should be, if it has changed velocity or heading in ways that outgassing cannot explain, then we will need to consider alternatives. This is the scientific method operating at its most fundamental level: observation, hypothesis, test, refine. We have observed anomalies. We have hypothesized natural and non-natural origins. Now we test. The universe will tell us the answer. It always does if we ask clearly and listen carefully. But the answer may take time. It may require data we do not yet have. It may involve phenomena we do not yet understand. And it may, though unlikely, force us to confront the possibility that we are not the only intelligence watching the skies, that someone else built something, sent it on a journey that took millions of years, and that it arrived here, now, in our system, for reasons we can only speculate about. That possibility is remote. Most scientists would place it below 1% likelihood. Some would place it much lower. But it is not zero. If you want to stay on the timeline as this unfolds, as observations come in and the story develops, it is worth following the data as it emerges. Institutions will publish findings. Preprint servers will host rapid analysis. Professional journals will run peer-reviewed studies. The information will be public. You can track 3I, Atlas, in real time using tools like NASA's Eyes on the Solar System, which provides interactive simulations of its trajectory. You can monitor astronomical telegram bulletins for breaking observations. You can watch for JUICE data releases from ESA. The next 4 months will either confirm that we have seen a truly exotic but natural visitor, or they will present us with data that cannot be easily explained within current frameworks. Either outcome is scientifically valuable. One is comfortable, the other is not. So here is the question to carry forward. When we observe something that does not fit our models, when we see patterns that seem designed rather than random, when we encounter the improbable stacked upon the improbable, are we looking at the far tail of a natural distribution, the unlikely but possible convergence of rare events, or are we seeing something genuinely anomalous, something that our priors have made us reluctant to recognize? That is not a question with an easy answer. It is a question that requires data, patience, and intellectual humility. It requires being willing to follow the evidence wherever it leads, even if it leads to uncomfortable conclusions. And it requires distinguishing between what we know, what we suspect, and what we fear. Right now, what we know is limited. We know 3I, Atlas, is here. We know it has characteristics that do not match typical comets. We know it passed through perihelion during an observational blackout in a configuration optimal for trajectory modification. We know it will re-emerge into view in mid-November. What we suspect varies by perspective. Most researchers suspect it is a natural comet with unusual but explicable properties. A minority suspects it may be something else. What we fear is harder to articulate, because fear in this context is not about immediate danger, but about the collapse of assumptions. We have built our cosmology on the assumption that intelligent life, if it exists elsewhere, is distant, rare, and non-interactive. If that assumption is wrong, if someone else is here observing us, perhaps deploying hardware in our neighborhood, then the implications extend across every aspect of civilization. That is not a fear of harm. It is a fear of irrelevance, of being observed rather than observer, of discovering that Earth is not exceptional or protected or alone, but simply one more inhabited world in a cosmos already occupied and monitored. Are we alone? That is the oldest question. We have asked it in every culture, every generation, every language. We have looked at the stars and wondered if anyone else is looking back. For most of human history, the question was philosophical, religious, speculative. In the 20th century, it became scientific. We developed tools to search. We built radio telescopes. We listened for signals. We calculated probabilities. We sent our own messages outward, and we found nothing. Silence, no response, no contact, no confirmed evidence of intelligence beyond Earth. That silence has shaped our expectations. It has made us skeptical. It has raised the bar for what would constitute proof, and that is appropriate. Science thrives on skepticism. Extraordinary claims require extraordinary evidence. The bar should be high, but the bar should not be infinite. It should not be insurmountable. If evidence appears, if data accumulates, if observations defy natural explanation, then we must be willing to consider that the silence may have ended, not with a radio signal, not with a message, but with hardware, with an object that came from somewhere else, that arrived in our system, that behaved in ways we cannot yet fully explain. 3I Atlas may be that object, or it may be a comet, rare and strange, but ultimately natural. The next 90 days will move us toward an answer. In the meantime, we watch the sky, we take the data, we run the analysis, we compare notes, we argue over interpretations, we publish papers, we present findings, we let the process unfold. Because that is how science works. It does not work through revelation or authority or consensus enforced by preference. It works through evidence, through testability, through reproducibility, through openness to revision. If 3I Atlas is natural, the evidence will confirm it. If it is not, the evidence will reveal it. Either way, we will know more in January than we know now. And that is the point, to know more, to understand better, to push the boundary of the explicable outward, one observation at a time. This is not a question of belief, it is a question of measurement, not a matter of faith, but of photons, of spectroscopy, of orbital mechanics, of chemistry, of statistics. The universe does not care what we believe. It cares what is true. And truth is found not by wishing or fearing, but by looking carefully and clearly at what is actually there. So look, watch as the data comes in. Ask yourself not what you want the answer to be, but what the answer appears to be based on evidence. And be prepared, as all good scientists must be prepared, to revise your understanding when the data demands it. Because something is out there. We know that much. Something came from another star. Something passed Mars, threaded the inner system, dove behind the sun, and will re-emerge into view in 2 weeks. What it is, we do not yet know. What it means, we cannot yet say. But we are about to find out. And whatever the answer, natural or otherwise, the fact that we can ask the question, the fact that we have the tools to measure and the frameworks to interpret, the fact that we are here, watching, wondering, testing, that fact alone is extraordinary. Not because we might have found something from elsewhere, but because we are looking, because we have become the kind of species that can detect interstellar visitors, analyze their composition, track their trajectories, and ask whether they are ours or theirs. That capacity, that ability, is the result of centuries of accumulated knowledge, generations of scientists building instruments and theories, decades of missions launched and data gathered. It is humanity at its best, curious, rational, rigorous, humble enough to admit uncertainty, and bold enough to pursue answers. So watch the sky, watch 3I Atlas, watch the data, and decide for yourself, are we seeing an anomalous comet, a visitor from a chemically exotic star system, a natural object at the far edge of the distribution? Or are we seeing something else, something sent, perhaps deliberately, perhaps long ago, to cross the void and arrive here, now, in our moment, when we have just barely developed the capacity to notice and ask the question? Contact or pattern seeking? Natural rarity or technological reconnaissance? The answer is coming. November 11th, December 19th, March 16th. The timeline is set. The observations are scheduled. The universe will provide the data, and we will learn, one way or another, what 3I Atlas really is. Until then, we wait, we watch, and we wonder, as humans have always wondered, whether we are alone in the dark or whether someone else is out there, looking back, perhaps from behind a disguise we are only now learning to see through. That is the question. The data will answer it. Soon,